All right, let's go ahead and go over this. I would like to determine the rate law for this problem. In doing so, I need to determine the order of the reactants for hydrogen and oxygen. I'm going to pick trials number 1 and 2, and in doing so, which substance am I going to be able to determine the order for? The oxygen. I'm doing that because it'll make it easy, because the hydrogen will not affect the rate. So when I go from here to here, I get a 3 times change. And when I go from here to here, I get an 8 times change. Is that correct? 9? 9 time change. Oh yeah, 9 times. That looks good. Okay, so I tripled the concentration, and that resulted in a rate that is 9 times faster. So my rate goes up by 9, my concentration only changes by 3. So the order for this particular substance is what? It's second order. Okay, so we just determined that my oxygen is second order. Great. A little problem with this next part is that there's no time when the oxygen is held constant. So it's going to be a little bit difficult to determine the hydrogen, but not impossible. Since we already know what the oxygen's order is, we can still determine the hydrogen's order. So I've got a tripling of the hydrogen's concentration. I've got a doubling of the oxygen's concentration, and this changes by a factor of 108. So that 108 change, was that only because the hydrogen concentration went up? Only because the oxygen concentration went up? No, the concentration of both went up. So this 108, part of it is because oxygen went up, and part of it is because the hydrogen went up. So we need to pull the oxygen part out, and we can because we already know it's second order with respect to the oxygen. So if I double the concentration of a second order reactant, how will that affect the rate? It will make the rate go up by 4. So the rate difference between the first and third trial goes up by a factor of 4 because of the oxygen. So that leaves a lot left over. So let's figure out exactly how much that is. 108 divided by 4 gives us 27. Or the other way to do it is that factor tree method, where I take 108, I pull a 4 out, and that leaves a 27 behind. So how much did the hydrogen change the rate? Changed it by a factor of 27, right? So hydrogen is responsible for a 27 change, oxygen is responsible for a 4 change. Okay, but I had a tripling of the hydrogen concentration, so when do 27 and 3 equal each other? When I cube that. So that just made my order with respect to my hydrogen a 3, third order. Second order with respect to the oxygen. Okay, so we're going to want to calculate out the rate constant. And so my rate constant is equal to rate, I'm just going to pick the first trial. So I'll say 580 divided by 2 squared times 4.5 cubed. Does anybody have that number?
1.59122.
Say again?
1.59122.
1.59. Okay. How many sig figs do we have?
1.6.
I was gonna ask that, how do you know, like,
Isn't it 2 sig figs?
2?
2.
So those ones, and the oxygen column, and
Yep. And the hydrogen also has 2. And the rate also has 2. Because it's only 580. Right?
the first filter.
Yep. Okay. So then my rate law is the rate is equal to 1.6 hydrogen cubed oxygen squared. And that's it.
Do you write it like that, or do you put in 4.5?
No, that's how you write it. That's what it is, period.
Okay.
That applies for anything. So now that I have the rate law, what does that do for me? What would I use it for? I can plug in any numbers I like, and that'll tell you how fast. So if I want it to go at 4,000 molar per second, I could plug those numbers in to get myself 4,000 molars per second. I would know, I could calculate the concentrations of each of these to give me 4,000 molar per second. Or if I had this concentration and that concentration of hydrogen and oxygen, I could immediately just throw in the calculation to determine what the rate is going to be with those concentrations. What if I didn't choose trial 1 to do this calculation here? It won't matter.
You would just have to make sure you.
I'm gonna get a number. If I plugged in, say, the second trial, I get a number really close to 1.59. And if it's not exactly 1.59, you can calculate all, in this case, 3 trials and then average the 3. So, it should be good. Where'd that bracket go? If I add calcium metal to a solution that contains iron ions, will any reaction occur? What would you need to determine that answer?
The table and the notes.
You need a table of the activity series, and when you look at the activity series, who's on top, calcium or iron?
Calcium.
Calcium. So what we have here is this calcium atom has his electrons. I know that because it's a metal. And this iron is missing its electrons. I know that because it's an ion. Okay. So if I'm a metal and I'm above another metal on the activity series, I will give my electrons to another metal below me. So since the metal above has its electrons and the metal below is missing its electrons, the calcium will give the electrons to the iron. So will a reaction occur? Yes. Calcium will send electrons to the iron ion. This is the only instance where electrons will be transferred. This is the only instance where anything's going to happen. If that iron was iron metal instead of iron ion, nothing would have happened. Nobody needs any electrons. If it would have been calcium ion and iron ion, nothing would happen because nobody has any electrons to give. If I add magnesium metal to a solution that contains sodium ions, will any reaction occur? So this magnesium, he's got his electrons, and this sodium is missing, but the sodium is higher. So even though the magnesium has electrons to give sodium, not only does sodium not want the electrons, magnesium wouldn't give it to him anyway. So no reaction is going to occur here. We got a nickel magnesium galvanic cell. All right, so. Say nickel to nitrate, and we'll go with magnesium nitrate. Okay, so which direction are the electrons going to go?
From the magnesium to the nickel, right?
From the magnesium to the nickel. So really, really specifically, it's going to go from the magnesium metal that's here, sending the electrons over. How many electrons is it going to send? 2, because it's magnesium. And these 2 electrons, where are they going to go? This nickel with a +2 is going to grab them, and now there's another nickel atom that has just been formed on that nickel bar. So how could this battery go dead? Sure. So all of this magnesium bar disappears that's under the water. I hate that. All of this all of that there dissolves away. These ions that are inside of the nickel solution there aren't any more atoms to gain the electrons. So I have to have a metal that's missing electrons and a metal that has electrons to give. So if these disappear, the other thing is if my salt bridge runs out of ions. The shorthand notation for this would be magnesium solid turns into magnesium ion divided by a salt bridge, and then nickel ion turns into nickel solid. And the voltage, what is the voltage for this? So we're talking about nickel. So the nickel is gaining electrons. So that's a negative 0.23 voltage. And the magnesium is giving up its electrons. And that's a 2.38. Um, 2.15 volts. Good voltage. Phosgen is produced by reacting carbon monoxide and chlorine gas together. So carbon monoxide and chlorine gas. Write the balanced chemical equation. This is the reaction that was used by Haber to kill the British troops that were in their foxhole. He had CO in a container and chlorine in a container, and when the plunger went down, the two mixed, made the phosgen, and then it slid across the ground and killed those guys. Pick two metals from the activity series, write down what initial conditions must be required for a spontaneous reaction between these two metals. Write two more metals which no reaction would occur. Okay. So I've got, I don't know, let's go with zinc solid and copper aqueous. And so then I have zinc aqueous and copper plus copper solid. Why? The zinc has its electrons, the copper is missing its electrons, and zinc's higher on the list, so it's willing to give the electrons to the copper. So that is a reaction that does happen. Right, two more conditions where no reaction would occur. Okay, so zinc solid and copper solid, and no reaction occurs because nobody needs any electrons. And zinc aqueous and copper aqueous. The copper would really love to get some electrons, and the zinc would like to give it electrons. It's just that it doesn't have any electrons to give. Write the equilibrium expression for this reaction. So K is equal to carbon dioxide concentration squared, carbon monoxide concentration squared, and oxygen concentration. And then for the above, calculate the equilibrium constant. So in this case, K is going to be equal to 0.032 squared divided by 0.0025 squared times 0.0016. What'd you get, Nikita? Wait, who did that problem? Is that you? What'd you calculate? I don't remember. 1 times 10 to the 5th, really? $102,400? Yeah. So I've got 2 sig figs, so it'll be 1.0 times 10 to the 1, 2, 3, 4, 5th. Answer the following. Okay, so I add hydrogen. How is this going to shift this? So if I increase my concentration of hydrogen, I'm going to get this reaction to shift to the left. So if I remove acetic acid from this, how is this going to cause? So there's my acetic acid there. So if I remove acetic acid, I'm also going to get a shift to left. So what Le Chatelier's principle is stating is that if you do something to an equilibrium, a reaction that's in equilibrium, it fixes that. So for this first example here, how did we mess up this equilibrium? I put hydrogen, now it has too much hydrogen. So what does the reaction do? Gets rid of it. How does it get rid of it? It takes the hydrogen and the acetate and makes acetic acid. And the next one, I took some acetic acid out. So I removed some acetic acid, so the reaction needs to make more acetic acid because some's now missing. And it does that by taking my acetate and my hydrogen ion and shifting it back over to make more, to replace the acetic acid that was just lost. Okay.